Thank you, organizer, for allowing me to present my work on prediction of crack path in reinforced cement concrete using acoustic emission analysis. Myself, Vivek Vishwakarma, I am a research scholar at Indian Institute of Technology, Roorkee. My research supervisor is Dr. Sonali Sare. Uh, I will start with a problem statement uh, for the motivation of this study is that uh, this is the part of a wider study which I am carried out for my PhD work, in which my specimens are going to be submerged in saline solution. So I have very limited options available for crack path monitoring or crack attributes monitoring. So this problem statement was to uh, monitor the crack propagation in RCC structure. So there are two methods which are widely popular in case of RCC structure, which are used in laboratories for crack path monitoring. That is digital image correlation and acoustic emission technique. There are a few other methods also, but uh, they have their challenges. So, since my specimen are will not be visible once I load it to the machine because they are submerged in water, saline solution. So, acoustic emission is the only possible solution which I have for monitoring crack development because it is a passive technique. It will not interfere with your mechanical loads. So my objective for this study is to predict, to develop a probability-based approach so that I could predict the crack propagation, or rather, I would say simulate crack propagation in lightly reinforced concrete beams based on the parameters AF and RA. So I will try to apply that approach to fatigue loading also. Before starting an overview of acoustic emission, it contains a piezometric sensor which can capture the elastic waves generated during the fracture events. It is a very sensitive instrument which can capture even micro cracking. So this is the general workflow of an acoustic emission technique. But why it is complex? Why it is complex? Because concrete is a highly non-linear material, heterogeneous in nature. Even the fracturing process is highly non-linear. It creates a fracture process zone while developing a crack. So there is a part of traction-free crack plus a fracture process zone, and there would be some micro cracking. Lots of micro cracking activities happen simultaneously in concrete structure. So it actually poses a challenge when you are performing acoustic emission analysis. So my aim was to create a simple method, not going for very high-end machine learning approaches which are present and high-end parametric analysis. My aim was to create a simplified approach. So I have used the traditional parameters available in literature, AF and RA. This is the definition. I will not go into it, but AF and RA are the parameters originally proposed by Ono and Otso, the Japanese researchers, long back. They have done the study on this, and they have concluded that the tensile crack actually is associated with a P wave. So these are the some parameters. There are many more parameters available for acoustic emission analysis. So for characterizing a tensile crack, generally a tensile crack generate a P wave type acoustic emission where you have high peak amplitude and low rise time, whereas other modes like shear cracks or friction happening in the structure, it is associated with high rise time and peak amplitude. This is the basic uh, approach which they used. So I am going to use that approach only. So it has a wider acceptance in the community, and it is simple and it is easy to implement, but it has its own challenges. We will see it later. So before starting with my data analysis methodology, a brief about my experimental program. So this is a part of a wider study. So these are some lightly reinforced beam. Lightly reinforced beam. These are lightly reinforced because to make them fracture sensitive. As we know, RCC is not a fracture sensitive material. Uh, it fails with yielding, but to make it fracture sensitive, we have to reduce the reinforcement ratio. So this is a very lightly reinforced beam. This is the acoustic emission sensor placements which I used in my experiments. So this is the basic mechanical monotonic load case behavior of my lightly reinforced beam. The testing arrangement, it is a CMOD controlled test, CMOD controlled monotonic test, uh, in which I can divide its mechanical behavior in three zones. The first two are linear zones. This point actually corresponds to when the crack actually crosses the reinforcement. Crack starts happening and it crosses the reinforcement. This point signifies this. This is the simultaneous cracking of concrete and the strain in steel, and this is purely governed by the yielding of reinforcement. So why it is important in my studies? Because almost all of the acoustic activity happens in these first two zones, because concrete cracking is taking place in these two zones only. There are very few events available for yielding zones. Why I am saying this? Because the approach which I am going to propose is actually a data sensitive approach. It gives fairly good results when you have enough amount of data. So in RCC structure, uh, there is no problem of getting acoustic emission data because it comes in a huge quantity. So this is the monitoring setup where monotonic load is applied. The crack is generating, concrete cracking is happening. These two figures are synced with time. This is not, so please don't get confused. In yielding zone, there will be very few events. So almost 78% of events are acquired up to this point. Okay, so I have used six R15 sensors. Now, a very important point, the sensor should be of similar sensitivity. Why I am saying this? Because those who perform acoustic emission analysis know the sensor sensitivity will actually control the quality of your data. So they should be of similar sensitivity. So location accuracy is calculated in terms of root mean square error from the pencil break test. So I have performed multiple pencil break tests on the specimens and compared the real location with the acoustic emission locations and found out the RMSE. I will show the significance of RMSE later on. So how this approach, how this data analysis methodology work, it is divided. I have divided into three parts. First is you have to do clustering. You have to characterize your events in tensile crack and other crack opening modes. Why I am focusing on tensile cracks? Because concrete is very weak in tension compared to its compressive strength. It is almost one tenth, and the whole fracture behavior is governed by tensile strength, the tensile cracks. So I have used a based approach. There are other algorithms are also available, like k-means. They are hard clustering algorithms. This is a soft clustering algorithm where every data point is assigned to every Gaussian. Gaussian mixture model actually divides your data points into several Gaussians. So using this clustering method, you can divide your data set into clusters of similarity. So by this, you can find out the range of AF and RA, find out the range of AF and RA, and why I am using GMM? Because concrete is a highly non-linear material. Cracking is also a highly non-linear cracking in concrete, and acoustic emission data is stochastic in nature. By the looks of it, you cannot find it. You have to perform some signal processing techniques to get out some meaningful results. So after doing clustering, we can step forward to spatial binning and temporal binning. So What is this? This is dividing your space into multiple bins. Uh, if the bin size I have selected is equal to the root mean square error in that direction, this is x direction. Uh, can you see my mouse pointer?
Yes.
Okay. So this is x direction, this is y direction, and this is z direction. So from the looks of figure, you can ask that why I have not done the binning in x direction, because this is a single crack problem. This is a lightly reinforced beam. So there is no need to do binning in x direction. But I have done it in y and z. If you have multiple crack problem, you can do binning in x direction also. So the major benefit of doing Gaussian mixture model is that you can further filter your selected events. When you have identified a tensile cluster, you can further filter it. I have applied a filter of probability greater than zero 0.8. So any data point which have probability greater than zero 0.8 of being in a tensile cluster, I have selected it for further analysis. This is also temporal binning, where the data is divided into bins of time. And if you average the y coordinate, you can predict the crack length also. I will come to it in later part. So these are some results. So for monotonic load cases, the blue curve is of DIC and red curve is for acoustic emission. The simulation of crack path is fairly accurate, and it can capture the path of crack, the curves of crack also. Uh, and added benefit over DIC is that you can get the depth data also in the Z direction also. So if you do pinning in Z direction, you can simulate the crack planes also. DIC will give you only surface measurements, and in case of concrete, because there is no out of plane, very negligible out of plane movement, so you cannot employ 3D DIC also. So acoustic emission gives you a benefit of simulating 3D plane also. Uh, Shifting to temporal binning, here there is a catch. You have to apply a physical constraint on your AE data, because you are simultaneously receiving acoustic emission data from all the points of fracture process zone, and there will be points uh, which are below the crack tip, there will be points which are above the crack tip. So uh, you have to assign a physical constraint to get a meaningful curve out of that. So I have applied a monotonic constraint, means a concrete cannot heal on its own. It is not a self-healing material. So at any instance of time, the crack length can remain constant or it can increase, but it can never be decreased. So this monotonic constraint help you to visualize your data in a meaningful way. So if you see the curve, there is a potential underestimation of crack length. This is the original crack length at this point of time, but the A is predicting a little, not little, a little less crack length. So this is actually the problem of averaging. You are averaging your data over 100 seconds. So this is going to introduce some bias in your results. So I'm trying to refine this, and hopefully I will do that. Now, in case of spatial binning, I have suggested that the bin size should be equal to root mean square error. But in case of temporal binning, this approach is not sensitive to bin size. It is sensitive to quantity of data. You can reduce your bin size as uh, much as you want, provided you have enough data available in your bin. And that is the reason you see at the later part of this curve, where the yielding is happening, you have less quantity of data, and here the underestimation. So after this, how I have tried to apply this in case of fatigue loading also. So I have performed some constant amplitude fatigue loads on the load ratio zero point 0.6 and zero point 0.7. All other testing arrangement and testing setup was same. But I have not employed DIC in case of fatigue loading because it is very data intensive task. Uh, So if you see how can we approach this, when we have done the monotonic load case, we have fixed the range of AF and RA. I am going to use those range because we use those range of AF and RA and simulate the crack path. So if you could zoom to one, this is the crack path. It is able to capture the path and with fair accuracy. But in case of crack length, there is a point to note is that you see there is variation in crack length. Why this is variation in crack length? If you see up to 80, 90 mm of crack length, this is predicting somewhat similar. But after that, the variation starts because if you see a fatigue curve, a crack growth curve, it has three zones. First is rapid growth, then stable growth, and then rupture. So when your material is in stable growth zone, the quantity of data is going to be very less, and that's why you see these variation. So I will reiterate that I'm trying to refine this, how to tackle this problem. So I will conclude my presentation and discussion with these points that GMM excels at handling in inherent randomness of concrete, cracking, and AE signals. It actually provides us the uh, greater understanding of crack development compared to hard clustering methods like K-means. Because it is a probability based clustering, which actually enables you to further filter your cluster data, which is not available in hard clustering. So, enhanced crack path visualization with spatial binning combined with crack mode classifications. It enables a clearer visualization of crack propagation in the situation where you cannot see your specimen. This study, actually, in first slide I have told you, this study was the outcome of a problem where I was not able to see my specimen. It is a computationally efficient because it is a parametric based method. It is a computational efficient and it can be applied to real time applications also because modern AE curves, modern AE softwares allow you to take out the data while doing the test. And it is applicable to complex loading condition with some correction. The approach successful in simulating crack path in monotonic load case as well as fatigue loading also. The crack length is underestimated and is dependent on quantity of data. So I will finish my presentation. Thank you.